A real molecule can be in any orientation to your view. Of course, not that you can see it. However, we have certain formal methods to depict molecules on paper or screen. This is the wedge dot and is very common. If we rotate about the carbon 1 axis by 120 degrees clockwise, 2 moves to the original 4 location, 4 moves to the original 3 location, and 3 to the 2 location. Naturally, this can be reversed with a 120 degree anti-clockwise rotation. The 3 substituents exchange positions. These 2 representations are the same molecule. Here we have the mirror image. It's an enantiomer. If we rotate the mirror image by 180 degrees, so it's still the same molecule, we've placed 2 of the substituents, 1 and 2, in the same location in both enantiomers. But now it's clear that the difference between the enantiomers is the exchange of 2 of the substituents' locations, namely, in this case, 3 and 4. An older method for depicting molecules was developed by Fischer. Again, exchanging 3 substituents results in the same molecule. When we look at the mirror image, we have the enantiomer, and here again, 2 substituents have been exchanged, that is, 2 and 4. So, in both wedge dot and Fischer representations, if you swap 2 substituents, you get enantiomers. But if you swap 3 substituents, you get the same molecule. Enantiomers have the same physical properties, except with respect to optical activity. And that was discovered by Biot. So, what does optical activity mean? Enantiomers can rotate plain polarized light. Light has properties that means it can be regarded as a wave. The waves can come in multiple planes that can be represented by a double arrow. Let's break down ordinary light into some of its planes. The first step in studying the optical properties of an enantiomer is to place a filter in the path of the light that only lets through one wave plane. Now we have plain polarized light. The plain polarized light is passed through a solution of the sample to be analyzed. If an enantiomer, so optically active, it can rotate the plane of the light as it passes through the solution. How do we measure this? There is now a second filter. It is physically rotated until the polarized light at this new plane can pass through, and a detector then can observe the light. Thus, the angle between the 2 filters informs us of the magnitude the sample has rotated the light, and whether the second filter has rotated clockwise or anti-clockwise to permit the plain polarized light to pass through is also important information.